in your web access page, I will now set this up so that each week has 2 blocks, and each block has the topics that we're planning to cover, and would also have the class notes from the previous class. Okay, so that would now be available for you. Questions? Okay. What's this? Ooh. All right, whatever. So I think we left off talking about implicit and explicit solutions, so we'll carry on from there and start talking about, well, we still quite haven't finished the first section, so we'll finish up the first section and we'll jump to the next section and we'll get going with this stuff. Let's take a look at this statement still from the first section. When we're solving for a differential equation, process takes us, so we do an antiderivative or an indefinite integral. In doing so, we got an arbitrary constant, right? So I have to take some points off for those people who forgot the plus C on their quiz. Speaking of your quiz, we need to practice some integrals. I wasn't looking at you. No. So here's what I'm going to do. I'm going to post the quiz up online. If you want to, if you think you did not do well on the quiz, you would probably want to download it, do that quiz over the weekend on your own, and submit it to me. Okay?
What if you did well, but you think you did well?
Well, if you think you did well, then you don't have to do it, and I'll keep your original score. If you redo the quiz, I will grade it again, and I will take the average between your new quiz and the score that you got on the quiz originally. Okay? And then I'll take the average. Okay? But I'm not going to give you your score or your quiz back until we do this. Okay? So I'll leave it up to you how you want to deal with that. And when you guys submit the quizzes, I'll collect it, grade it, and then I'll figure it all out and put the scores up. Sadie? It'd be, just bring it. Print it and bring it. Okay? All right. So back to this statement over here. They're talking about arbitrary constants. So when you create an arbitrary constant, we have what's called a one-parameter solution. It turns out that when you have several higher order, an order higher than 1, you would probably do several integral processes. You'd probably have to integrate more than once. And when you do that, you create more arbitrary constants. Okay? And so when that happens, then you have a 2-parameter family of solutions or a 3-parameter family of solutions, depending on how many times you integrate. And then a solution to a differential equation that has no arbitrary constants is a particular solution. That probably means if it has no arbitrary constants, it probably means that you had already solved for that. So let's take a look at a simple example. Let's take a look at how position, velocity, and acceleration interacts with each other. And let's start off with a differential equation that says the second derivative of position is equal to an acceleration. And let's take a look, for simplicity's sake, let's take a look at a gravitational acceleration. And I'm not going to use units right now. So let's just say the gravity is 9.8, and that is your acceleration. So this is a differential equation. It's an equation. It has a function that we're solving for that has at least one derivative. In this case, we have two derivatives. So if we integrate both sides with respect to t, we have on the left-hand side, the antiderivative of the second derivative is just probably going to become the first derivative. So I'll just write the first derivative there, x prime of t. Oops, I don't need the dt anymore because I already did that operation. Do you guys know what the integral of 9.8 is, the integral of a constant? 9.8t plus c, right? So this is your arbitrary constant. Now, I still have a differential equation. It's still a differential equation, so I have not completely solved for x yet. But I can do that with just one more step. So let's take the integral of this again. And then what I would get here now is the integral of a derivative is the original problem, or the original function. So that would be x of t. Now I got x of t all by itself. And now I would integrate this. The integral of 9.8t is what? So 9.8t squared over 2. You guys didn't want to put 9.8 over 2 in your heads and figure that out? 4.9. That's a pretty popular one. You'll see that a lot in physics and Calc 3. C is a constant. What's the integral of a constant again? ct. So, but I'm integrating this. This is another indefinite integral, so I need to come up with another constant. So I can call that d, or maybe I'll just come back and call the first arbitrary constant a c1, and then call the second arbitrary constant a c2. So now I have a two-parameter family of functions, and the parameters are based on the arbitrary constants that came up when you were doing the antiderivative, the indefinite integral. So we would call this a two-parameter family of solutions. Now, our next section, this is hard to introduce new material because in order to tackle more of this information, I have to kind of jump to the next section, which is what I'm kind of going to do. If I give information about the x prime and the x, I would be able to solve for C1 and C2. And that's how I would be able to get a particular solution, is that if there were initial conditions, that's what it's called, and we'll define that later on. If there were initial conditions, I would be able to solve for C1 and C2 so that I can figure out what the particular solution is. So I feel like this definition should belong in the next section, but they put this here. So I'll leave it at that for now, and we'll get to the next section in a few minutes. So let's move on and take a look at singular solution. So a solution obtained from a family that cannot be found by assigning a value to an arbitrary constant is called a singular solution. So they have an example here. And let's see how this is illustrated. So let's take a look at this particular differential equation. We don't know how to solve for it, but let's just say somebody solved for it and then they got this. So a solution is y is equal to this thing. Now the question is there another solution? We should probably check that this is in fact a solution. You guys know how to check, right? And just put it back into the equation, which means I need to take the derivative of this thing and set that on the left-hand side, and then take this and multiply it by x. Yeah?
Are those C's the same, or are they C1, C2?
These C's, I think, are the same. So the question is there another solution for this? Remember that other solution, the trivial solution? Remember a trivial solution? What is the trivial solution? 0. Did 0 work? Looks like it, right? So what if y was equal to 0 and y prime is equal to 0? If I put 0 in for y prime and 0 in for y, that looks like it will work. Okay, so it says a solution obtained from a family that cannot be found by assigning a value to an arbitrary constant is called a singular solution. Hey, wait, what's that mean? A family means there's an arbitrary constant, so there's a whole bunch of different possible solutions.
So that's looking at like plus C.
Yeah, the plus C makes a family of solutions.
And then C1 and C2 would make it two different families.
It would be a two-parameter family. Yeah, let's not worry about this. So the last thing they talk about in this first section is a system, and this is something that we'll see at the very end of the semester if we have time. And so I'll just put it in our notes and not really talk much about it because we need to move on. A system of ordinary differential equations is two or more equations involving derivatives of two or more unknown functions. And a popular example of this would be like the population of a couple of animals that are living together in an environment or something like that, like predator-prey kind of relationship. Give me an example of a predator-prey relationship in an environment. Fox and rabbits. So let's say F would be the population of foxes. And then R population. R would be the rabbit population. And both of these would be at some time t. So we can say that these are dependent variables. These are functions that are dependent on some time t. And so one can say that the rate of change of the population of the foxes, so df dt, is equal to, is dependent on the population of the foxes plus the population of the rabbits or something like that. And usually these things have constants. And let's see. Usually there's like constants and stuff. So let's say the population of the rate of change of the population of the rabbits is dependent on twice the population of the foxes minus 3 times the population of the rabbit, or something like that. So if you put these two equations together, you get what's called a system of differential equations. We have 2 or more variables. We have f and r. That involves derivative of f and r, and then we're trying to solve for f and r. So in solving for one of these things, you will need a little bit of linear algebra with matrices and stuff like that, but we'll introduce that if we as we go along. So I don't know. In the past, I never really got this far in this class, but I think this is one of those important ideas to be able to cover. So I'll try to make sure that we cover this. All right, that's just an introduction to another type of differential equation, since we're all classifying them and stuff. All right, questions? Let's move on to closer to actually doing some of these problems. These are, this is a big introduction to a lot of things we're going to discuss, and we're not really going to be solving for differential equations until like middle of chapter 2. So the next section talks about initial value problems, or IVPs, they're called sometimes. An nth order initial value problem is an nth order differential equation subject to a set of conditions called initial conditions, or ICs. And usually they tell you to solve the initial value problem, which means they would give you a differential equation, and they would give you an initial condition or a set of initial conditions, and then you need to figure out what the solution is. And in doing so, you'll end up finding a particular solution. So an example of this would be going back to our position, velocity, and acceleration problem. And what I could do is to set up the initial value problem, your IVP would look something like this. You need a differential equation which is what we started off with last time. But now you also need initial conditions. Now, however high your order is, the order of your differential equation, that's how many initial conditions you should have. So let's say the initial velocity is equal to, let's say this was thrown somewhere, so initial velocity is 4.1, and then the initial position, oh sorry, I should call this x of 0, and that initial position is equal to 10 or something. So with these two pieces of information, I have my IVP. So IVP has two things. It has a differential equation, and it has initial conditions. And with this, we can answer whatever question they're asking and be able to find out our solution, our particular solution. So if you remember our halfway solutions that we were working on, we got x prime of t. Remember what that was? 9.8 t plus, and then we called it c1, and then we had our x of t is equal to 4.9 t squared plus c1 CT plus C2. Okay? So now, supposedly, with an initial condition, with an initial value problem, we should be able to figure out a particular solution by solving for C1 and C2. So what we can do, see, what does that mean? What we can do is, it looks like we could put 0 in for the t values, and then your x of t, x of 0 would become 10. And then it looks like if we put in 0 in your first derivative equation, we should get this thing to equal 4.1. So let's see if that'll work out. So let's put 4.1 in for t. So x prime of 0, I'm sorry, you put 0 in for t. We get 9.8 times 0 plus C1, and this is supposed to equal to 4.1. Right? Did I do that right? So C1 equals 4.1. Well, that was easy. So now let's take our second equation, x, the position itself, and then put 0 in for t. Oh, we know 4.1, so we can replace this with 4.1, right? I guess it didn't matter because I was going to put 0 in for t, and that would disappear anyways. And then if I put 0 in for t into the x function, that should equal a 10. And so I have 0, 0, and C2 equals 10. So it looks like I have a particular solution . And the particular solution is x of t is equal to 4.9 t squared plus C1, which somebody found, or we found to be 4.1, plus C2, which we found to be 10. So here is our particular solution now. It's a solution that should work in this initial, you should work with this differential equation. If we were to take the derivative twice, we should get 9.8. And it has no more arbitrary constants because we were able to solve for those arbitrary constants. Okay? Okay, questions? So, if you have taken physics or Calc 3, this should be really familiar. This is equations of motion. All right, let's take a look. So as a math class, the next theorem here is really important. But we're kind of not teaching this as a math class. This is more a class for engineering people. And the existence of the uniqueness theorem basically just guarantees that if you have these conditions, that you're guaranteed a solution, and your solution is going to be unique. So the existence part means you're guaranteed a solution, and the uniqueness part means that's the only solution that works within that domain. So let's read through it. R is a rectangular region in the xy plane defined with x between a and b and c between y and d. I guess we should draw this. It contains the point x naught, y naught in the interior. So not on the boundaries, but directly in the interior. If f of x, y, and the partial derivative f with respect to y are continuous, so you got a couple of conditions here, and the f that they're talking about is dependent on your differential equation. So all those derivatives, all the derivatives, basically if you have a nice function, and we all have nice functions. We all have nice functions. Yeah, all the functions that we've been dealing with since pre-calculus are all nice functions. The logarithm function, they're all nice as long as you're not talking about, you know, the places where they're undefined or anything like that. So as long as we have a nice function and we're dealing with a bunch of nice functions, then we can say that these things are continuous. Then there exists some interval within here, an interval that's near x naught or y naught. Should do this in a different color. So we have a small distance h here, so x naught minus h, x naught plus h gives a little small interval in the x-axis where your graph or the function itself, here the solution, exists and is unique. So this is your solution curve. So that means you're guaranteed a solution within that interval, and within that interval, that solution is unique. That means that's the only solution that would work. I don't know if that made sense. Does that make sense? No. You could have, yeah. You can switch the y-axis. But, yeah, you can do that. Yeah, no, don't think of 3D. All right. Again, this is not going to be that big of a deal. I think there might be one question in the homework assignment that might ask you something about this. But we do care about, what I want to care about is the idea of where our domain exists. And for that, you need to remember your pre-calculus, like what's the domain of the logarithm function, what's the domain of the exponential function, the domain of especially those rational functions when you have x in the denominator and you don't want x to be equal to 0. So we'll see a few of those examples. In fact, I think maybe we should take a look at a homework problem. I think I had a homework problem that I was interested in doing. Yeah, let's take a look at the first one. So we have a couple of problems here. It says y equals 1 over 1 plus c1 e to the negative x. So there's one arbitrary constant here, c1, and so this is probably going to be, it is a one-parameter family of solutions of the differential equation, and then they give us a differential equation. So find a solution for the first order IVP, initial value problem, consisting of this differential equation and the given IC, initial condition, down below. So These are two separate problems, so let's take them one at a time. So it looks like for this one, if this is our solution here, what we want to do is we want to assume that this is, if this is our, you use x, right? If this is our x value, then your y value is, that's negative 1/3. So what I would like to do is I would like to take our solution, our family of solutions. Oh, wait, before we do this, you guys want to picture this? It's always nice to picture things. Let's picture this. Look, I got a graphing calculator here. Y equals 1 divided by 1 plus C1, I'll just put C, times e raised to the negative x. Oh, C is equal to 1. What if C is equal to 2? It looks the same. I know what. Let's draw a bunch of them. Make it look like a whole family. So this looks like our family of curves. Wait, I'm just putting positive numbers here. We could probably put negative numbers, right? Let's try another one. See if we can put a negative number in there. Whoa. Looks like some of these have asymptotes. Yeah, they just shoot up, right? I guess that would make sense if e to the negative x here times 3 becomes negative 1, then that would make the denominator equal to 0. Whereas if you're adding the denominators, so e to the x will never be 0, e to the x will never be negative, so there's no chance for the first few denominators to be equal to 0. So it looks like our domain would work for everything there. So we could take a look at this and say, aside from being cool pictures, we can say that this looks like it's a family of solutions, right? A one parameter family of solutions. That's so cool. Let's take a picture of it and put it in our notes. Okay, that didn't work. Let's try it again. So what we want to do, essentially, is if we identify our x to be equal to 0 and a y to be equal to negative 1/3, we should be able to find one of these specific solutions. One of them would work, right? So let's continue looking at the graph here. What if I plot my point? What's my point again? 0, comma, what? Negative 1/3. That's right here. That's hard to see. So the question is, what value of my C should this be for me to be able to hit that graph or to hit that point. So let me see. So there's a cool way to find it using this program. Let me start by clearing some of these things. And make this a parameter. That goes from -3 to 3. So as I move my parameter, oh, I didn't hit it. I need to go further. So as I move my parameter somewhere along the way, I'm going to hit that point. You see that black point over there? So right around here, you see it? Right around here, I would hit that point. So there's a couple of, aside from hitting that point, there's also another important part to this, this solution, is that this graph over here on the left-hand side becomes discontinuous when it goes all the way up to 1 1/3 about. So we should keep that in mind as we're trying to find the solution. So it looks like the C, which is this number over here, should be about, well, it looks like it's -4. I'm looking down at the bottom here. C is equal to -4. So let's, that's the graphical perspective of this. Let's see if we actually get -4 when we solve for this. Did anybody solve for it already? Yeah, okay. So we're going to take this equation, the solution. We're going to put y is equal to -1/3 and x is equal to 0 and see what we get. So y is equal to -1/3, and that's the left-hand side of this equation. We have 1 divided by 1 plus c1, which is what we're solving for. E to the -x, and x is equal to 0 in this case. So e to the 0 is 1. And for this, maybe I'll do some cross multiplication. Maybe I'll bring this negative sign down to the 3, so when I cross multiply, I won't have to deal with it too much. So this is -3 is equal to 1 times 1 plus c1, and c1 after bringing the 3 over, or after bringing the 1 over, becomes -4. So there we go. Just as we suspected, it turns out to be -4. Okay? Any questions? The graph was cool though, huh? All right, let's take a look at the next one, and I won't actually do it. But just by looking at these family of curves over here, and you know these curves that kind of go from the negative x-axis, it goes up to, it looks like an asymptote of maybe 1. We should know what the asymptote is, right? But anyways, the asymptote, the horizontal asymptote at 1. All these graphs over here are when c is bigger than 0, it looks like. And then these graphs where it breaks apart is when c is equal c is less than 0. So looks like my point here is x is equal to what? -1, y is equal to 2, right? So -1, 2, oh, 2 is way up here. So does it look like these curves would work? These curves over here? So these curves over here, when c is bigger than 0, looks like it's it's kind of trapped. Your y is trapped between 0 and 1. And when c is less than 0, it looks like I go down below here, and then I come back up here. So I don't know. This is going to be kind of hard to get. You think? You think we'll get it? Let's see. I guess we should actually do the work here, huh? So y is equal to 2 is equal to 1 over 1 plus c1 e to the negative positive 1. So it becomes a positive 1, right? Negative, parentheses, negative 1. So I guess we can cross multiply again. We got 2, 1 plus c1 e. So I'll just call that e to the first power, is equal to 1. Distribute 2 plus 2c1e is equal to 1. I'm solving for, what am I solving for? I'm solving for c1. So I need to subtract negative 1 and then solve for c1. So c1 is equal to what? Negative 1 over 2e. Anybody punch that in the calculator and tell me what you got? What? Negative 0.184. Negative 0.184. So small value. Let's take a look at the graph. So we have a different point now. Our point is, what was it again? Negative 1? Negative 1, 2. Can't see it up there. Let's try the slider first to see if we're going to get there. Oh, yeah, we do get there. Well, what did we get? Negative 0.18. 2. There it goes. Now it looks like it's passing through, right? If we got that solution that we just got. So that particular value for C1 out of these infinite families of curves, this particular curve gets it. Okay? So, suppose I should have taken a picture of the other one also, but let's take a picture of this one and discuss what it means see if I can squeeze it in our busy page here. Doesn't go. So, this is our graph, and we said that this is equal to negative 0.182-ish. That's our value for C1 that would give us that particular solution. One of the other questions that they ask usually is that what is the largest interval that would carry this, that would have the solution? So let's add on to this question, what is the largest interval? For this solution. And it turns out that the largest interval would be the interval where it's continuous around there. So remember that existence and uniqueness theorem that says that you're guaranteed a unique solution within some closed interval and then between some value of h. So this is really, really small, and I meant to do this in purple. So negative 1 comma 2. What interval can we have for this particular curve that would for this particular function to work? So it looks like there's a discontinuity here, and then if we can go on forever, we can go on forever, and it will remain continuous. Okay? So for us to figure out the largest interval, we want to know where there's a discontinuity and pick the part of the graph that contains the point. Now, there's another smooth curve on the left-hand side of that discontinuity, and if our point was over there, then we would pick that side. But now our point is over here on the right side of this discontinuity. So for us to figure out that interval, what we need to do is we need to figure out where this discontinuity happens and then solve for that. And let me call it A. This is your asymptote. And your largest solution is going to be for x. Are you guys familiar with this symbol? It's an element of. So x is an element of, and then this continuity starts from a, whatever a is, and it goes on to infinity. You can find a, can't you? So this is this equation. Y is equal to 1 over that business. It's basically this equation where C is equal to this. So you just need to figure out when the denominator is equal to 0. That's where the bad point happens. Okay? Any questions?
So when you're looking for the discontinuity for the denominator, like because you're gonna have two unknowns.
Well, your C1 is here.
Okay, so from that point,
Well, let's find it. So this is our y is equal to 1 over 1 plus, and then we found that to be negative 0.182 times x, right? Oh, e to the negative x. So basically what we want to do is we know that this is going to be discontinuous when the denominator is equal to 0. So let's just focus on the denominator and set that equal to 0. So 1, I'll just put minus 0.182 e to the negative x equals 0. So that's where the bad point happens. And then we just solve for x. It looks like we need some sort of logarithm here. So you guys can figure it out. Well, C1 was arbitrary, but now we're focused on one particular solution where C1 was equal to this. Yeah. So if I was looking at this problem over here where C1 was equal to negative 4, that's a different problem. And that has a different discontinuity. Yes? Vertical asymptote. Oh, VERT. Maria is used to my writing already. I'm hoping that you can get used to my writing within a few weeks. could type it out. That's a lot of work.
A is 1.6. You could always erase it and leave negative 1.
Did you get it? Negative 1.69? All right. So usually when I ask for an answer, I didn't ask for an answer, but thank you anyways. Usually when I ask for an answer, I ask for 2 people. So you guys both did it separately. Same thing? 1 point, what is it? So A is about negative 1.69. And so your interval is going to be from negative 1.69 to infinity. So that means your solution, your particular solution, is good for any of these values. And it's not good for anything less than that. So I can't say, so if this is my solution, what if I try to put negative 2 in there? Negative 2 doesn't fall under there, so we can't use that. Okay? All right. Let's see what's next. Boundary value problems. We'll talk a little bit about boundary value problems later on, but the more popular types of differential equations are IVPs, where they have initial values. And the boundary value problems only happen really in special cases, and they happen when we have a second-order differential equation. Sometimes a higher-order differential equation, but this is where we're going to apply the boundary value problem. So here's an example of a boundary value problem. We have a differential equation, and instead of your initial conditions being at y and y prime, your initial conditions happen at y at some point and y at another point. Or it could happen at y prime at some point and y prime at another point. So you see the difference between initial conditions and boundary conditions? So a boundary condition has 2 different x values, or independent variables. Independent variable values. So it has 2 different x values using one function. When I say one function, that means a function and not a function and a derivative. Just a quick reference back. I'll come back to that page. But our IVP has an initial condition for the original function and as many derivatives, 1 less than the original order of the differential equation. And furthermore, it's using the same x value for those initial conditions. Whereas a boundary value problem uses the same function and then uses 2 different x values or independent variable values. Okay? So this is an example of a boundary value problem. Like I said, we'll only approach this in a special case when we're talking about the second order differential equations. Okay, questions? All right, let's see if the textbook has any problems that are relating to the boundary value problems. Let's see if we could do one of those. Oh, I think I was going to do number 11, which isn't a boundary value problem. It's an IVP. Did they have boundary value problems here? Which one?
39.
39?
Yeah,
Oh, that's a pi now. All right, let's do one of those. Let's do number 39. So we have a solution to a differential equation. It's a two-parameter solution. Y is equal to C1 cosine 2x and plus C2 sine 2x. And it's a solution to this differential equation, y double prime plus 4y is equal to 0. If possible, sometimes it's not, find a solution of the differential equation that satisfies the given side conditions, the boundary conditions, basically. The conditions are specified at 2 points. They're called boundary conditions. Yeah. You want to see it in the graph form? No. All right, let's just solve for it and move on, huh? All right, let's just solve for it and move on. Okay, so what we want to do is we want to take our y function, this is our y function over here, and put 0 in for x. When you put 0 in for x, your y should equal to 0. So using this first condition, boundary at 0, we have 0, I'll put y first, C1 cosine 2 times 0, so that's just 0, plus C2 sine of 2 times 0. And I hope you know what the sine and cosine of 0 are. And using the next condition, y, and this time your x is equal to pi over 4. This is C1 cosine 2 times pi over 4 plus C2 sine of 2 times pi over 4. And after you calculate that, that should equal to 3. Okay, so what two equations are we solving for? We essentially now have two equations and two unknowns. And our first one is, what's the cosine of 0? 1. So that's C1 times 1 plus the sine of 0? 0 is equal to 0. So C1 must equal to 0, right? I have cosine of pi over 2. I multiply this, I get pi over 2. C1 times cosine of pi over 2. What's cosine of pi over 2? 0 plus sine of pi over 2. And that should equal to 3. So given these two equations, if you solve for them, you get C1 is equal to 0, C2 is equal to 3, and so now you have a solution. So the particular solution, I should spell things out first before you get used to my handwriting. Particular solution is going to be y is equal to C1 was equal to 0, right? Should we write that or just leave it? And then C2 is equal to 3, so that's 3 sine 2x. So the particular solution to this boundary value problem is y is equal to 3 times sine 2x. Okay? So that's how you would solve for boundary problems. And for these types of differential equations, this is essentially the same way you'd be solving for the initial value problems as well. Because initial value problems, you'll come up with a pair of equations with two unknowns like this and then solve for it. Any questions? All right, let's continue. Let's see, do we want to do any of these other problems? Nah. All right, let's take a look at the next section is actually now an application section where you're going to need to try to translate words into these mathematical equations. And it's kind of like those applied problems that you have in algebra and calculus and stuff. So the key thing about these problems is that you'll always see the phrase rate of change of something. Because in modeling in this class, what we want to do is model differential equations. And differential equations, you know, are equations of where you have an unknown function and you're finding the unknown function. And in the equation, you have derivatives of the unknown function. So when we talk about derivatives, the phrase rate of change refers to the derivatives. So usually when they talk about the differential equation, when they first introduce your very first differential equation that you solve is like a population or growth and decay type of problem. And the differential equation is described by, maybe I'll just type this one out. The rate of change of a population or something, I'll just say population, is proportional to the current population. So this is usually the first and easiest kind of differential equation that's introduced when we first do an example of a differential equation that we're going to solve. And the idea is to take this phrase and translate it, like word for word, like you're translating another language. So now we're going to translate this language in English into another language in math. So how are we going to do this? Back in algebra, or even the pre-algebra courses, I usually have my students look for the verb in the sentence, and the verb is usually the verb to be, and that usually becomes the equal sign in math. So when you're able to identify the verb, anything on the left side is going to be the left-hand side of the equation, anything on the right-hand side is the right-hand side of the equation. So let's say that this translates to an equal sign. Now, here is the rate of change, the key phrase rate of change. And sometimes it says rate of change, sometimes it says something that's kind of synonymous to that. But in general, that's what you're looking for, the rate of change, how something is changing. And that means derivative. Derivative of a population. So my dependent variable must be the population. And so why don't I just call that P? And we're changing, and let's just say we're changing with respect to time. Usually, when I say with respect to, WRT is how I would say with respect to. So my derivative then becomes, I want to use Leibniz notation here in this case, becomes what? dp dt the derivative of the population with respect to t is equal to now. So this isn't just equal to, it says is proportional. So proportional. Do you guys remember the proportional business? To the current population. So the current population, to me, I think is just P. P is the population, so let's just call it the current population at a specific time t. So this proportional to means I need to come up with a constant of proportionality, right? We use alpha, I think we use k. Let's use k. So dp dt equals what? K times p. Okay? So this is our differential equation. And if we know a little bit more about this, like at a time 0, let's say the population was 300 or something, then I would come up with an initial condition. Can I just put IC, initial condition? So possible initial condition at time 0, or at the beginning of time. Let's say this is a population of bacteria in a dish or something. At time 0, we have there are 300 in your population. So giving this piece of information would allow us to solve for the unknown constant. So without this, the solution for this differential equation would be a family of curves, would be a family of functions, but with an initial condition, we would be able to solve for that family of curves, for that arbitrary constant, and then call it a particular solution. Okay? And also this constant of proportionality, you'd be able to solve for this constant of proportionality if you have another piece of information like, you know, after 10 minutes, this petri dish has so many bacteria, whatever it is we're counting, whatever population we're counting. Okay? All right. So now that we've written this, and this is probably going to be covered a little bit later on, but now that we've written this, let's actually look at it. And do you remember where you might have seen this before and what the solution might be? Calc 2? What's the solution to this? E to the kt, and then k would be positive or negative depending if this is a growth or decay. The initial time is going to be the coefficient of that thing. Okay? So I'm not so interested in that solution, but let's do it right now. Let's see what kind of mechanics in this class we're going to learn. And the first kind of technique that we're going to learn in this class in terms of solving for this, we haven't solved the differential equation yet. But the first technique that we're going to learn is called a separable differential equation. And the separable differential equation is when you're able to separate the dependent variables with the independent variables from the independent variables. Okay? And what that entails is an abuse of Leibniz notation where we take the dp dt and actually separate it. Now, in calculus, I think maybe you were taught to say that this stays together. You can't separate them. But for the sake of a technique that we're going to learn called separable differential equations, we're going to allow ourselves to separate this with dp on one side and dt on the other side. So what we're going to do is separate the dp and dt. So I'm going to bring this p on the right-hand side, divide by p on both sides. And I'm going to take the dt on the left-hand side and multiply by dt on both sides. Yeah, so, and then we're going to integrate both sides. So in doing so, we have successfully separated the variables, and that's why it's called separable. And then now, if we integrate both sides, they have their differentials ready to be integrated as well. So I'm integrating the left-hand side with respect to p, and I'm integrating the right-hand side with respect to t. Okay? Now, when I do that, you remember what the integral of 1 over p is? ln p. Thank you. Now, this would generate a plus c, but I'm going to erase this. Yeah, because there's going to be a plus c on the other side as well, so why don't I just like kind of merge those plus c's together? So let's not worry about that plus c. Now, a constant with respect to t, what's the integral of that? kt plus c. So I'll just say that this c on the left-hand side kind of merged with the c on the right-hand side and keep everything on the left-hand side. Right-hand side. Keep all the c's. Now, in general, you want to solve for the dependent variable p, right? P looks like it's the dependent variable. And so it has an ln in front. So what do? Take the e of both sides or use the whatever you call it. So I'll just say p is equal to e to the kt plus c. That kind of looks like the solution that we mentioned, that we saw from Calc 2. Or maybe even in pre-calculus. I guess when you study this, I've seen some pre-calculus books where they introduce this equation over here, but they don't do any calculus. They just come up with this as a solution. Actually, they can't introduce this because this involves a derivative. Never mind. Anyways, this is our solution. It looks very close to what we were saying, except we are supposed to have a coefficient in front of e to the kt. But it turns out that e to the kt plus c is the same thing as e to the kt times e to the c. And, well, why don't we just call this p sub 0. So then p of t is equal to p sub 0. That's actually e to the c, right? But let's just call it p sub 0 e to the kt. So that is our solution to our differential equation. And this is our first real differential equation problem where we're actually using a technique that we're learning in this class called separable differential equations. Really important that you know how to integrate. Okay? So there are other types of applications. Radioactive decay, for example, is proportional to the amount that's remaining. Let's do one more real quick. Oh, we're past time. Newton's law of cooling. So this section 1.3 discusses all kinds of scenarios where you would translate your English into a differential equation. And then they're not asking you to solve for the differential equation because some of these being translated are going to be tough to solve for. But hopefully you can get some practice into translating from English to our differential equations in math. Okay? So that's it for now. Good luck with your homework. The bookstore will have the code and or the book for sale on Tuesday next week if you're trying to get it through the bookstore. If not, just buy it online. Okay?